Alright, so I'm going to go through this as quick as possible. So my background, I started programming at 16. I used a tool called Blender to do all my 3D artwork. That was a free tool at the time. It was the best tool, and that's really pretty much been the best thing in my career. And someday I'll pay back to their fund like thousands of dollars because it's really made my career awesome. I got a bachelor's in real-time interactive simulation. They originally wanted to name the college as a video game something, and they're like, oh, we couldn't get that through the state, so they called it real-time interactive simulation. Its nickname is Nintendo University. It's out in Seattle, Washington. It's by the Microsoft campus, and we used to share a building with Nintendo. So, my other background, I've been building my own game engine from scratch over 20 years. It's all C++. Anything from animation. Later, you just open a notepad and start from zero code and build a game engine. So that's my background. I've been working to kickstart a pinball manufacturing company, Pulaski Pinball. I'm building my own circuit boards and stuff. I want to build a affordable pinball company. So everything's going up. Jersey Jack games are going up to like, God, 15, 20 grand some of these games. So I want to be like 3 grand or under. So I'm building everything in house, and that's my target goal, is to be under 3 grand. So I'm also a 3D artist and software engineer. These are just a couple things I pulled off from my portfolio. So again, all built in Blender. This is a sculpted head, and a lot of this other stuff is what they call box modeling. I've moved all my texturing to be in a program called Substance Painter. It's a really good tool. It's procedural creation. We'll go into that in a little bit. Let's see. So this was just a couple clips of things I worked on in my own game engine outside of my professional experience. So this is a robot that I created and animated. Somebody did the concept work. So this was supposed to be like I call it a boss planet. It's just like you fight a bunch of bosses, and it's supposed to be like a quick game. Here's a real-time RTS game that I was working on. You can see airplanes flying around, and different AI and nukes that you can fire off. Again, I'm trying to start a pinball machine company, so there's some of the boards I built, and there's the game that I've been showing off at Free Play for a couple of years, and wasn't quite ready to show it off yet, but we're getting really close. Again, my experience, I worked on a couple of the Madden games. Killing Floor was a zombie shooter game. I worked on porting that from PC onto PlayStation and Xbox. So there's different things in the software realm that you have to consider for that. I was talking to this guy, when you port to the Wii U, it didn't have a vector processing unit, so you can't do multiple instructions at once, so you kind of like cut all your processing power down. So you can't draw as many models, you can't do as much physics. You know, when you're talking about the football game, you know, you got all these bones and joints. When you're talking about like a first-person shooter, you don't have as many. You probably just have a hand that's, you know, you don't care about the physics in the helmet and all these things. So you have to cut back on some of the physics and try and optimize the code for that. I've worked on like the crowd system in PGA, the rendering of all the crowd. Maneater was another game I worked on that a lot of people seem to know about. So you're a shark and you swim around and attack boats and stuff. So I worked on like the bounty system for that. They called it like Grand Theft Auto. So yeah, you would whip the boats, and I worked on where the guys would like hit the shark off the boat. The bounty system where they actually came out. The quest system, which was if you played it, and like the tutorials, teaching people how to play it. Currently, I'm on NBA 2K. I'm an AI engineer. I've been there for 3.5, almost 4 years. I do a lot of player interaction stuff, so we're taking motion capture data. If you've ever seen a movie, you know, they have all these white dots on you. I don't deal with animations with the face, but it's usually just the dots around here. They might do a motion cap session twice a month or so. Again, a lot of the stuff I do is, they call it the ambient system, so it's, you have motion capture of guys high-fiving and different things, and you know, if you make a shot here, it's not going to align perfectly to the motion capture data we have, so we kind of have to like tweak you to line up, so when you play these two animations, the guys will actually high-five and their hands will hit, because if they're off by a couple centimeters, they're going to miss. So we're doing all this like data processing. We have a huge collection of animations, and we have to figure out which ones, you know, based on kind of like distance and rotation to the other player, how those are going to align and interact. So there was a clip of two guys clapping hands there. So we start with a 2D world. So this was, again, the Boss Planet game I was showing you guys. I had reached out to an artist I work with. I said I needed some concept design, and I gave them a few, I think maybe like Dead Space or something. I wanted a female character that was like sci-fi. So some guy that I work with drew up these concepts. Eventually I get those back and I kind of pick the things that I like and kit bash them together. So I came out with this concept and did some kind of paint overs. And then I sent that actually to another artist. So on the left, you see a high poly. We call it the high poly. This is like, I think 2 million triangles, and the one on the right is like 15,000, 12,000. So what's on the right is actually what we render in game. On the left, it's what we use as artists to build a nice detailed version. And then what we call it, we can bake it down. You'll see in a minute here, but just to give you an idea of the art side versus what actually goes into the game and we're going to run processing on. And there was just a final textured version. So if you know like the kneecaps and around, I guess it's kind of hard to see with the contrast, but when we bake it down, you see kind of some of the final details actually make it on like these little rivet holes there. So 3D world, you know, how do we see all these games? So it's basically models, textures, and lighting. That's where it all comes down to at the end of the day. There's a lot of other complex things that happen there, but when we talk about creating a model, here was a model that I created, again, in Blender. If you guys are interested in getting into modeling or level design or anything 3D, Blender is really nice to use. It's free, and it's been supported for years. It's getting better and better. So, again, Blender 3D. So right here, this is, just to give you guys an idea, that model is 21,837 triangles. And I'll just show you like a super quick process of how we would start modeling that. So here I already have the model, but I created it from some 2D references. So this is kind of like a little bit easier here, but we create a couple cylinders, like for the engines there. And we just create some planes and squash them down, some boxes. And then we're gonna line them up. We can taper off the end there. We can duplicate the wings and mirror them. And you kind of see it's basically how everything starts. It's not gonna look great like the one on the left because I'm doing it in like 3 minutes, but you know, even the cylinder here, it's like, it's only got 8 sides here. It's an octagon versus the other ones that are really high detail just to give that shape of the actual X-wing. And then we can extrude different parts and make the windows. So the one on the right looks not as good, but it gives you an idea of what you can do in a couple minutes. And I think that model took me about 20 hours to actually make. So
I have a question about the model.
Sure, go ahead.
So like when that model on the left, the more detailed one, does that combine the textures with the model? Like how complicated is the model versus like the texture that you map to the model?
We'll go into that. They're two completely separate processes, right? So there's just the geometry, like if I model this chair, it's just gonna be gray, right? If I wanted to get you in a game, like, you know, in NBA games we actually scan people in, everything's just gray. It's just a triangle. We'll get into that, but the detail is as much as you can put into the image to make it look nice. It's that kind of, again, we'll kind of go a little bit further, but you can put a lot of detail into like making all your fingers and wrinkles, but when you're talking about the texture, it's just the visual appearance, just to make it have color, kind of essentially. So again, we take that model, that 3D model, I put it into a program called Substance Painter. You can see on the left here, it's kind of hard to see, but all the red outlines are just the triangle, so you can see kind of the detail. On the right is the actual representation of the colors and textures being applied to it. So normally you can actually click a button in Blender, which I do a lot of times because I'm lazy, and it'll just take all of that triangle data and put it over here and unwrap it so that it fits into the image. And you'll see, like, right, obviously the UV coordinates here, this maps to there and back and forth, so when it goes to render in real time and you're flying around, it's just doing a lookup to say, hey, like, what pixel should this color be? And it goes and maps back here, essentially. Again, on texturing, orientation doesn't matter. We're just doing a lookup. We have a triangle, so anytime, any rotation in the 3D world, this pixel right here is going to always map down to here. what time is it?
10:17.
Oh, we got plenty of time. So when we started 20 years ago or so, you're talking about, you just had like one texture basically. You're talking about Doom. You just have a diffuse color. It's just straight up surface color and then maybe some lighting that they bake in. So nowadays you have, gosh, up to maybe 8 different textures that represent different data. So one of those would be color, right? So here you can see there's no actual lighting happening down here. Everything looks really flat. Also, the tool that I was telling you guys that I use is called Substance Painter. A lot of this detail right here in like the edges, like scratched edges for guns and ships and stuff, a lot of that's procedural. So you can actually take that 3D model into the program and then you just drag like, hey, this is a scratched metal surface, and it already knows like all the edges. So like all this work I'm getting for free. Like this model, if I didn't have that tool, this model would look terrible pretty much because I'm not that invested in art. I'm in the engineering side. Again, there's other pieces of data like roughness. So when you're flying around the world, when you think of surface roughness, thinking glass versus concrete, like this is black because it's 0, so it doesn't have any roughness, that the windshield's going to reflect 100%, versus like some of the engines have some rust, so they're white or they're very rough. Let's see. So you also have surface direction data. So this is important for lighting. As you can see here, like green is Y, the Y-axis, and some of the rendering programs is up. So if your light is up there to the sky, the sun, and this is pointing up, then that means it's basically 100% lit, and it'll be super bright. And if it doesn't have any Y, if there's no green, so this is pointing down, it'll be lit separately, or lit dark. So this was just me showing a sample of this X-Wing in real time in the tool, so I can use Substance Painter. If you take a note, so first of all, there's only like 4 triangles right there, if you can see them on this panel right here. There's a triangle here and there, and then as you see when I rotate the view, you can see there's certain areas that are more highlighted and not, because each pixel has like a representation of surface and dust and different reflective properties, so you can see each one of those pixels was more reflective or not. And then I told you guys like the windshield was black, so it's going to reflect basically up to the sky or whatever's in the world. So again, one of the things I worked on was the crowd system and the PGA golf game. So when we first started doing that, I think we had 20,000 people in our test demo. So these are all mostly individually animated people. We might have, you know, maybe up to 10 different like idle animations. Where, you know, you don't want every single crowd member to rock like this in sync. So we would take a sample of maybe like 10 seconds or so, and then have 10 different animations where they could loop from different time stamps, so that everybody's kind of doing their own different thing. So each of the guys isn't actually doing, you know, they're not actually smart AI agents where they're trying to like path around and eat popcorn, and every guy's doing their own thing. So the main point of this too, also, we're going into a concept called level of detail. So if you look at this image here, right, you can't see anybody's eyes, any ears, nose, anything. So when people are that far back, we don't actually load like their nose and stuff. Like, we don't draw it at all. We just draw like, a lot of these people, their hands are just squares, and their shoes are just really junky shoes.
What is that method called again? I forget what it's called, where you have kind of like a step level of detail.
Yeah, level of detail, we call it a lot.
Yeah, quick question. So when you were showing the X-Wing, and
Yep.
working on texturing for that, so is the process of taking those textures and putting it on like a 2D plane, like a UV map, is that done automatically?
I usually let it automatically happen. It just depends on what the model is. Sometimes it takes time. If you're in a professional environment, yes, right, you're gonna mark every single edge and you're gonna unwrap it, because you wanna make as much use of that space as possible. When you do like in, again, he's talking about, there's a process here, right? So 3D models, when you gotta map it to the actual 2D images that you're gonna put onto them to render, all these triangles here, you have to actually do some work to map it into here, and you wanna pack it in. So like if there's a little screw back here, we want it to map to like a tiny little spot here, but the main big surface here, it takes up a lot more of the image. So again, the tool I use, a lot of times you can literally just hit an unwrap button, and I think that was the result for that. I don't think I did anything manually to try and like make it any better or pack more. Because you could just take, just to give you an idea, you guys could take all of this and just scale it down to half the image and only use like a quarter of the image. It would be terrible. Your model would look horrible, and you're not using all the other textures. So all of this would, basically you're looking at like a really low res photo versus a high res photo mapping onto your model. So again, what you were mentioning, we call it LOD, or level of details. Here is a car model that I worked with on a game that I was working on. And you can see the tire treads here, the rims, and you have all these screws and details. And then as we go down, the car and the wheels, they step down in their triangle count by a lot. And here you can see the actual, yeah, I mean, you can see like the treads are gone, the rims don't have any more of the stuff, because you're seeing it up close, but really you would switch to this model, you know, maybe every 50 feet you're gonna switch to a lower res, like I said. You can't see somebody's nose 100 feet away, so at some point there's a transition where you'll get a pop. If you pay attention to any game, you'll see like where it'll just basically pop. You can be smart about that transition, but...
So how expensive is it to do processing to interpolate between the different models?
You don't really interpolate. So interpolation would be, he just means kind of like tweening, like how do you blend as that happens and not make it pop. It really depends on what you're rendering. You could do that with certain models, but terrain is one where they do it usually a lot, because you can see like a cliff in the background just kind of like pop a little bit, but yeah, usually it's just a snap. You literally just one frame, it's the high res, and then it's a step down. Because even if you look at this right here, all of these cars actually kind of look the same. I'll show you the overview again. But they all kind of look the same from a distance. And just to give you an idea, that was 25,000 triangles there, and I think the lowest one, I'm going to say it was probably like 4,500 triangles versus 25. So you're talking about computers that have certain processing. So if you're taking a 20,000 triangle model down to 5, you just cut the processing power by 4. So you can render different things. So like if I'm up here close to a wall, or like a concrete wall or carpet, you can have what's in front of the player really close, more detailed, and then everything in the background is just way less detailed. But on level of detail, what I was saying is like, from here, the pop doesn't really matter, because I could literally just move any of those interchangeably, and I don't think you would see very much pop. Okay, again, most of my time is spent engineering, so just to give you guys a little bit of in-depth on how engineering is. When you look at this was just on Newegg, I picked a processor. You look at the 3 main things here, which is L1, L2, and L3 cache. A lot of people think nowadays, oh, everything is 32 gigs of RAM, whatever. We're still, as engineers that are building real-time games where every single frame we're rendering millions and millions of triangles and performing physics and all this stuff, we still are kind of really trying to write code that is super fast and works with 384 kilobytes. That's kind of like the difference between a real-time system and a non-real-time system. L2 cache goes up to 6 megabytes, and then L3 for this one is 32 megabytes. So just kind of a general thing on this concept of cache. You have this RAM over here, it could be up to 32 gigabytes. Let's say you're running a game on your computer and then you watch a movie on YouTube for 2 hours. when you come back, everything takes place over here. All the operations, all the mathematics. Yeah, everything has to be in this tiny little chip for it to operate on. So again, we run for 2 hours. Everything inside of our CPU that can do work, it's all YouTube content. So my game has been flushed out at this point. Now all of a sudden, I want to tab over and start playing my game. So this is Battlefield. This is a 64-player online game. Each of those players have data, name, number of deaths, health, their 3D location, their skin color, all their gear. There's just tons of data just for one person. And also take note, when you kill somebody in these online games, you have an icon usually here that shows up. So for the sake of this, what we're talking about cache, I said you had 384 kilobytes of cache, L1 cache in this CPU, the memory has. That's literally an entire icon. So we can't even load an entire player in this game into our CPU at one time just to perform some operations. So again, I gave the job, my code's gonna run right now that I wrote. It's gonna print all the players on the screen. Is any of the data in the cache? No. It's not an L2 cache, it's not an L3 cache. The CPU is stalled, it cannot do anything. So what it's gonna do is it's gonna put a fetch into RAM, it's gonna go to Windows. This all happens kind of under the hood. All I've done as a programmer is I just wanna address player 1 and then start looking through player 1, 2, 3, 4, 5, up to 64. But under the hood, it's got to go fetch this memory, my CPU is going to stall and wait, and then my code will start running again. So again, we do the fetch to player 1, it happens. Eventually it's going to load in. Again, I told you guys, there's 384 kilobytes of cache in the L1 cache, so literally just our icon can fit there. And this takes time too, right? We've sent a request to OS, it's got to go all the way through this electrical wire, all the way to RAM and back, and it's going to start loading this memory one by one. As that happens, while it's sitting, it's going to start loading other data sequentially as well, because it's going to assume that I'm going to start using all this extra data as I go on. So again, while I said I'm fetching this memory so I can operate on player 1, I still can't print his name because it started loading an icon that I'm not going to use. So we're still stalled waiting for extra data that I actually need to do this operation, which is print 64 player names. Again, cache versus RAM, the comparison here, right? 2 gigs, 32 gigs, we're still working with only 38 megabytes of cache. It's not very much memory. So what you should have learned from this is this would be a really bad example of how to store data for a video game. So if the start of our program is here, we'll just say that's 0 megabytes. If offset from there, we store player 2 32 megabytes away, 200 megabytes is player 3. So if we're scattering all of our memory, every single time I have to draw player 1 and then go to player 2, I'm stalled. My CPU is doing nothing, and it's just fetching all this data until it gets there. Then I can draw the player name. Then it's going to look for player 2 or 3, and they're not going to be in the cache, which means the CPU can't do anything. So that would just be like, nobody would do that, but that was kind of the idea of how the cache works. And yeah, so again, this would be good if you store all the players sequentially, player 1, 2, 3, 4, 5. Again, as I start to do operations on player 1 and I request memory about player 1, it will start loading player 2, 3, 4. It's just whatever is in memory next to there, it'll start loading that into the cache for me because it's assuming I'm an intelligent programmer and I'm probably going to do a loop through a bunch of things, whether it's a particle system, Sparks, just the next piece of data that I want is probably going to come right after, so it'll do that under the hood for me. And again, this is just an even faster idea. So we have this idea of the player data, right? We had icon, name, health, skin color, all this. If we actually wanted to make this a little bit faster, it makes kind of the programming side a little bit of a headache because you're scattering the data, but you can store the player's name and position separately from their icons, because their icons are just these really big pieces of data that we don't care about. You only care about it once when somebody dies, and you're only doing it for one player. So we store the data separately, so as soon as I do a fetch to draw player 1, all other players are going to load super fast. They're going to be in the cache and ready for me to print their names.
By that, you mean like having a struct of name, position, and a pointer to the icon.
Sure, you could have a pointer, you could do anything. You could just create a global variable that says player names and locations, right? And it could just be an array. So it could just be like 2 separate arrays, or the pointer, I can follow up with you later on that, but if you had a pointer, you still have a player and then a pointer in there, so you're still, it's still going to be bad, right? Because you still have to go to that pointer somewhere in memory, and you're still kind of loading the main player object. You're kind of separating the player object and having a pointer, and yeah, I'll follow up if you have any more questions on that at the end, but it's a little bit more in depth. Again, we go even further. Computers, CPUs have registers, right? So I talked about L1, L2, and L3 cache. We actually have just a couple of registers where we can actually do stuff and perform math, add, subtract, multiply. So just kind of like a visual representation of how small we're talking about in the CPU. And that was just a simple job to print names. So again, video games are doing explosions, there's thousands of sparks, there's all kinds of tanks shooting, physics, terrain deformation, all kinds of things. So that was really just a simple job, and you can see how slow things can go. So yeah, like a 5 gigahertz processor, you're talking 5 billion operations a second. Most games, they're rendering 60 to 120 frames a second. So you basically, if that was a single core processor, you only have 41 megahertz to update that entire game. Nowadays you have 12 cores, you're talking 5 gigahertz times 12. You also have dedicated audio chips, you have dedicated graphics cards, all your networking cards, they kind of do all these other jobs for you, right? Back on caches and CPUs and memory, remember, it's all electricity at the end of the day, so when you're talking about the CPU and all this memory inside of it, you know, we're talking about nanometers, right, and tiny little sections of space, so the L1 cache, for me to do operations in there, let's just assume it's a millimeter, but really it's sub-millimeter and a nanometer. Lost my train of thought here. Yeah, so if you're going to go to RAM, right, the electrical wire to hit the RAM, it might be 6 inches from your CPU board. So if that's 100 times more distance, an electron has to go there and back, and it has to do some processing. So you're talking about every time you have to go to RAM, it's going to be 102 times slower in that case, but again, realistically, we're talking about sub-millimeters, so it's like 2 million times slower to go and access the system RAM versus whatever is already loaded in the CPU. Another optimization every video game uses is called MIP mapping. Again, it's about being efficient and caching certain memories. So again, we talked about the crowd members. We don't want to load like high detail faces and noses. Not only do we not want to load their nose, we can actually use less resolution textures. So this was another model that I made. Here is like the high resolution one. You can see all the skin's wrinkles. And this image is, I think, 2048 by 2048. So it's 2,000 pixels wide. And when we zoom out and that character gets far away, like in the crowd, and they're 100 feet away, because they're smaller on screen, if they're only 10 pixels on screen, I actually only need 10 pixels to draw. I don't need to start, you know, walking through here and figuring out what's there. I just, you know, take these 10 pixels basically and plop them there. It's just more efficient, and it's going to load into like your graphics card's going to load that way quicker and render that object way faster, because you're talking about like 192 bytes versus 2 million bytes being loaded just to render something that at the end of the day is only going to be 10 pixels. We also do that optimization as well in terrain. So this is another idea of like how you have a smaller texture, same kind of thing with level of detail. So this was a terrain demo I wrote. You see it's patching in higher detailed terrain here as you get closer. Everything far away is like really less detailed, because I don't need to see every little crevice and rock way out there, because I'm just never going to see it. But as you start coming in closer and closer, you know, you need to start seeing a couple feet differential bumps. You know, if you're looking at a hill it's only like a little ant mound, you're not going to see it that far away, so you don't need that as much detail. So.
But couldn't we use the GPU instead of CPU to make it?
This is run on the GPU. Yeah.
Okay.
I mean, it's processed on the CPU. There's other different ways. This is just called geometry mapping. There's other ways that systems do this. Clip mapping is another one if you want to read up on it. But essentially, it's kind of like a high resolution mesh that's already pre-built that kind of walks around with you. This is kind of patching in different areas, so it's like a grid system where that's why you see like one grid just all of a sudden pops. But all of the commands to render the terrain still come from the CPU, right? So the CPU is determining what to draw, when to draw, and what level of detail you want, because the GPU's job is to draw triangles. It doesn't know anything about an AI crowd agent. It doesn't know where it doesn't have any idea if it's a human that is drawing. So everything is still going to come from the CPU and tell it what job that graphics card should render. Another concept to speed up rendering, backface culling. So here's a cube that has a bunch of triangles on each side. If we were to just kind of like peek through a hole in it, you would see that there's faces in the background. Since we can never see those surfaces always face away from our eye, we're not going to render them. So that's what they call backface culling. So if 3/6 of the sides of the cube are not drawn, we're going to save 32 triangles per side of this cube. So again, we're talking about efficiency and being intelligent here. Also, another thing that's very important is the order in which things are rendered. So in this case, we have a 1920 by 1080 resolution. We have 2 million pixels that we have to color in light. So this was just kind of like a level that I built, but let's just assume all this stuff happens. Let's assume there's shadows and everything that looks beautiful. All of a sudden, the last thing we render is a building right in front of it. So we just rendered all these characters, cars, we did all the surface reflection stuff, and then all of a sudden half of our image is this. So what we would do is every single frame in the game, or every other frame, or at some point we're going to reorder what we want to draw, and this building will always be rendered first in any game that you're going to play. Just an idea how much work it's done per pixel. This was a copy and paste of some code I wrote. So this code runs on my graphics card, and anytime a triangle gets drawn, it will have one of these programs running, and it'll figure out which pixel, like I said, every pixel that gets rendered gets mapped back to an image, and one of those pixels will give us information like surface color, reflection, and so here's what I'm doing. I'm saying like, hey, grab me this texture, I want to know the surface color, I want to know all this, and at the end of the day, we say final color that goes out to our LCD screen is right there. So it's a lot of work per pixel, and we don't want to waste all that time doing stuff that never gets rendered. And again, like I said, every frame, this is me from the other side of the building, so I would render the player first, then the car, then the building, and then the floor gets rendered last. We also, to speed up things, partition worlds. So here was like a world that I built. Here's a little character here, so you can see it's a pretty big, complex thing. There's interiors over here. There's a bunch of like boxes that can explode and go flying, and there's little spawn points for AI enemies to spawn. So yeah, again, there's just some like interiors. There's like doors and different panels and things. So there's a lot of ways to solve this problem, but one, we can just say, let's do a grid, right? So let's partition this up. My character was way down here. It's gonna take them 10 minutes just to walk this whole map. So first of all, if I'm not in this building, don't render or update anything in the building, right? Also, if I'm down here and I'm facing this way, I shouldn't render any of these grids behind me. So I could loop through, like, I don't know, maybe there's 10,000 objects in there. I could on my computer loop and go, hey, is this object behind me? Is this one, am I inside this building? Instead, I could just kind of look at the whole system as a grid and say, what grids can I even see? What should I even consider to render that's going to go on the screen? And the same could be thought of for like physics and other things. So if I throw a grenade in grid A, grid B that's 100 miles away doesn't need to like loop through all the players and see if they should blow up or should be dismembered. Cover all that. There's other things we can do too, like, you know, as birds or like crowd members get really far away, like if you really look at like Grand Theft Auto and you're driving through a city, you could see different things animate at different frame rates. So if you have birds like really far away and their wings, you know, because they're only rendering to like 10 pixels, you can render them at like half rate, so you save CPU cycles on maybe a bird that's right here that's like running in a puddle splashing around. Again, reject any grids that you can't see. You can partition worlds in different ways, but that's kind of the idea. And again, different games have different problems. Some in NBA 2K, we actually have like box collisions all up on our fingers. You know, as you're going and you're trying to swat the ball, you don't just want like a flat hand to go like this and then like collide with a guy's head and go through it. So we need to kind of deform the fingers all the way over the ball and the player. Whereas if you're talking about like a first-person shooter, we don't care about that. Or like the Man-Eater game I was telling you guys about. You're never going to be like really up close to see a hand or care about it. So we don't care about performing physics and making sure that when we eat them, like their hand conforms to the fin of the shark or whatever. Let's see. That's pretty much it. If there's any questions, I was just gonna show, again, like at the end of the day, everything's just triangles, right? So we're trying to put something on the screen. This is just a wireform representation of all the triangles getting rendered and animated. And yeah, that's pretty much it. Any questions?
Yeah, so you mentioned you've been working on or making your own custom engine. Is there like a specific shortcoming from commercial engines you wanted to address while like making your own?
I think one, I like building stuff. So again, like why build a pinball machine company? I don't know. I mean, no one's in video games. Almost everything's been done, but like for pinball, it's like, well, there's this. I think we could make a cheaper game, and that's something fun to do. It's, what do you want to do with your time? I try to keep busy. I noticed the speed at which if you wrote your own code and you want to solve a problem or you have a crash, the speed at which I do that at home versus work. Again, we were talking about Frostbite at EA and different things. It's like if I saw a graphics bug where a shadow wasn't working, that might take me a couple days at EA when I'm working on FIFA or something, or we share code with FIFA and the Madden football game. Something goes wrong. It's like both of these games are like one's working, one's not. I gotta go like load this up. Anyway, efficiency and stuff, but also learning. If you want a job in rendering but you don't know how to render and you haven't done it yourself, then who's going to build the next complex terrain system or something like that? Go ahead.
I'll just keep going. This is something that's popped up recently. Like, so as games get, like, the game worlds, right, get more and more complex, do you think we'll see a shift away from, like, traditional sort of like object-oriented programming to like entity component systems and things that are better and equipped to handle like large amounts of data?
I'm not sure exactly what you mean by so you're talking the CPU side and like
it's like there's a lot of games that have come up in the last few years where it's like they've essentially had to use like entity component system in order to keep everything running. A lot of voxel-based games. I think like one of the most recent Minecraft games made it. So I'm curious if you know anything about it, or like you see a trend towards that sort of setup as opposed to your traditional.
I mean, it's kind of hard to answer because when you say components and stuff, I mean every game I've worked on or whatever is going to be, you have a component attached to an object where it can run like independently of that object. But at the end of the day, if you have to do work that's collision work, it's going to happen somewhere. So you're kind of more talking, it sounds like talking about the structure, unless you're talking about voxels and like the world itself.
Yeah, mostly it's like, I'm talking about, I guess, structure, like ECS, so as opposed to like having every, you have a player object that has like a presentation actor and blah, 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 blah. You just have like an entity ID and then use that ID to look up, give me all the entity IDs that have like this property or this
yeah, I think you're kind of, you're talking about kind of doing like a lookup, like I said, where you had a player, and I separated all the data kind of, it's like, it depends what you're trying to do. Like, when you talk about the crowd rendering I did, where I said we had 20,000 crowd rendering people, those people actually get processed like, kind of like that, right? Okay. They're kind of just like bits. Yep. Like, this guy's a bit, like, is he in view or not? Then we're not going to render him, we just represent him as a bit, right? But then you have his other data like stored somewhere else.
I was just, sorry. I may be mistaken about what we were saying, but I think also maybe you might be referring to also something like in terms of how some people are trying to use toon shading for games in recent years, I think Zelda games they do kind of use tone shading
Right.
to simplify the details, so that way it won't look too complicated for calculation.
Well, there's a stylistic approach to that. You know, I just showed you a program that was like 100 lines of code. I can change that to just render it all like very cartoony and like, not, you know, I can change the lighting to look more cartoony, and I can actually put like an outline like around the character and make it stylistic. The other reason too is Nintendo's consoles are generally lower processing power, so a lot of their stuff is a little bit lower resolution detail, so it kind of fits, like the Zelda thing kind of fits that, right? If Zelda were to go full realism and like have the most realistic faces, it's just, you're kind of matching a completely different game, right? And hardware.
Yeah, the hardware option is because Nintendo's following the Gunpei Yokoi strategy. Pretty much they purposely put themselves limitation with affordable hardware power. So that's why they're like that. So they do it on purpose.
Yeah. Well, they also have like, you know, you can take the thing and it's a portable console as well, right? So it doesn't have as much processing power. It's got a battery you gotta consider. So I think when you take your Nintendo Switch and bring it off, I think it automatically tells you that it's in that mode, and you might, like I said, you might start drawing cars like at a lesser version automatically because it doesn't want to do as much processing power. It wants to cut down, you know, keep the battery life going. So, anything else? All right. Well, appreciate some people actually showed up, and